Good day, ladies and gentlemen, and welcome to yet another episode of our JG7's classroom. Now, it's been a while, apologies for that, but real life has been tough lately and time constraining. But anyway, today we have a special episode for you that we originally didn't intend to make, but since it is relevant, especially for World War II combat and specifically the late war period, we thought there is very little out there on the internet explaining high altitude performance or high altitude flying and fighting, and hence we decided to make 2 episodes out of this. So today's episode and the next episode are going to be about high altitude performance and high altitude flying. And in order to convey the topic and the message to you, we split the content into 2 episodes. So first of all, we are going to go over some theoretical considerations. That is episode 4, this one here. In 2 chapters, I will be explaining to you what high altitude flying is all about and how we can use this knowledge to derive fighting rules or fighting behaviors that may change or be different to what we do when we are down low, and to visualize these concepts. In the next episode we are going to go over practical examples. Now, as always, I am your host and instructor, Killerfliege, and I wish you a pleasant lesson. Alright, ready, set, go. Let's dive right into chapter 1. Let's talk about some performance considerations when flying at high altitude. And in order to understand how our aircraft's performance changes with altitude, we need to look at the environment that we fly in. Now, the environment that we fly in is obviously the atmosphere, and the atmosphere is governed by certain physical laws in terms of how pressure, density, and temperature behave with altitude. And there are several definitions for the atmosphere, or atmospheric models, if you will. I'm using the International Standard Atmosphere here to convey the principles to you. So as you can see, we have the units, or not units, quantities, air pressure, temperature, and air density, because all contribute to your aircraft's performance. Air pressure and air density have an influence on your engine performance, but also on your aerodynamic performance, lift generation. We have looked at that. And the temperature also influences the air density again and the air pressure, and also has an influence on your engine performance. Now, what you can see here is the trend of these quantities according to the atmospheric model. Who's interested in how to derive those? There is a mathematical model obviously underlying this atmospheric model, which is laid out here. Some of the initial values that you need to set are given here for your calculations. This is the standard definition. I don't want to go too deep into that, but what you should know and see is that, for example, if you take density and pressure, air pressure, both decrease with altitude. So we go up in altitude here. This is in meters. And as you can see here, we start at a higher value, and the higher we go, the lower we get in terms of our pressure and density. Bear in mind that in order to make these trends visible, I used 2 axes here. So the upper one is for pressure and temperature, and this lower one here is for density. So, but you can see both have an exponential tendency of decay. Now, in terms of temperature, at least according to the International Standard Atmosphere model, the temperature decreases up to an altitude of about 11,000 meters, it more or less decreases linearly. Once we are at 11,000 meters at some minus 50 something degrees centigrade or sub-zero temperatures, up to about 20,000 meters, the air temperature stays constant before it slightly decreases again. And this can be seen here in these equations. So as you can see, we have a starting temperature and we have a linear decay depending on our altitude difference. We have a constant temperature between 11 and 20,000 meters, and we have an increasing temperature, but as you can see, the increase is less than the decrease previously in terms of rate. Okay, so this is how the environment behaves that we operate in. Now, of course, there are variations in that environment, and what's also interesting is that air pressure, air density, and air temperature are related to one another via the ideal gas law. So the ideal gas law presents the relationship between pressure, air density, and temperature. And as you can see, it's a rather linear equation, and there's a coefficient here, which is the so-called specific gas constant. So with this equation in an ideal gas, you can, and it is, let's say, accurate enough to describe our atmosphere as an ideal gas, you can basically determine, if you know what pressure and, for example, temperature you have, you could determine the density and vice versa, because this is a constant and is usually known for all major gases that we can find in nature. Okay, now, as I said, the standard atmospheric model is just a model, and in reality there may be deviations to that model. So we might have local low pressure, low temperature regions, or high pressure, low temperature regions, or low pressure, high temperature regions, or high temperature, high pressure regions. So local deviations to our standard model that are also going to impact our performance. Okay, so this is wraps up the environment that we fly in. And now, in order to understand how our aircraft behaves inside that environment, we need to look at so-called density-altitude definition. So, the density-altitude definition gives you an idea how your aircraft performs. So how does it work? We've just looked at the standard atmospheric model. And in the standard atmospheric model, as you can see, for one specific altitude, for example 10,000 meters, we will find a specific air density value. Now, as I said, due to local variations, that air density value may be different. Maybe we are at 10,000 meters and we measure a density less or higher than the standard model predicts. And that is basically what density altitude is all about. It basically describes at what altitude your aircraft is, let's say, actually flying in terms of aerodynamic performance. Okay, so for example, here, as you can see, we are at a nominal height of 9,000 feet. And let's say we fly first into a local high pressure, low temperature area. What that does to the atmosphere in general, and using the ideal gas law, we will find that the density in this region would be increased. Because low temperature, shrinks the air volume, if you will. And that means the density in this region is more equivalent to a density you would find at 7,000 feet in our standard model. So in this region, despite being at 9,000 feet measured, our aircraft would behave as if it flew at 7,000 feet. And since we have more aerodynamic performance the lower we go, because the density is higher, we would expect in this region to have a better performing aircraft. So in a nutshell, an aircraft in this region would behave as if it flew at 7,000 feet. Now, if we fly into this region here, where we have a low temperature and high temperature and a low pressure, both resulting in, let's say, the air volume to stretch out a little bit, which in turn decreases the density, our plane may behave as if it flew at 10,000 feet, because the air density here more resembles the state in our standard model, or the air density at 10,000 feet. Okay, so in this region, essentially in our example, the air density, let's say, is equivalent or similar to the air density in our standard model at 10,000 feet. And despite being at 9,000 feet only, our aircraft behaves as if it was at 10,000 feet, and hence we have decreased aerodynamic performance accordingly, because lower air density. This is why we call this a high density altitude, because with respect to our standard model, we fly, or we feel like flying, at a higher altitude than we actually are. And this is a low density altitude. Now, a high and low does not refer to the density value, but rather the altitude where you would expect this density. So we have high density down low and low density high. So yeah, I know it's a bit mind twisting, but that's how it works. And we have a low density altitude because our aircraft behaves as if it flew at a lower altitude. Okay, so this is the concept of density altitude, which is also why you find density altitude values often in aircraft manual in graphs that are used to determine takeoff and landing performance. Okay, one more thing about the environment that we operate in, which is tactically relevant, and that is the phenomenon of contrails. Now, contrails or condensation trails are basically condensed water, so clouds basically, that your aircraft produces. How does it work? Well, your aircraft spits out gases and particles from the combustion, so basically combustion products, and these little particles can serve as condensation seeds that the water vapor in the atmosphere can adhere to and then form clouds or condensate. Okay, and depending on the outside conditions, you see those contrails or you don't. And there usually is a band or a range, altitude range, in which aircraft produce contrails, and there's going to be an altitude below that where this is not the case, and an altitude above that where this is also not the case. So let's call this the contrail area. How they are created, I've already told you. And that sliver of contrail area may move. It's not always constant. It depends on the current atmospheric conditions, and it may move along the altitude axis. So in winters, you would find contrails occurring at lower altitudes because the air is usually cold and wet, so it makes it more prone to condensate, or for water vapor to condensate, whereas in high temperature scenarios, the air can take more volume, let's say, of water vapor, and hence it's a bit more difficult to make the water condensate, because it need the air needs to be saturated for condensation to happen. Anyway, this is something you keep in mind for the following reasons. Obviously, once you are in the contrail region, you're visible. So these clouds that form, you all know this, look up in the sky, watch some airliners. These clouds are visible from quite far, so it'll be much more difficult to hide or run a stealthy attack when you are in contrail. So that's why we talk about this and why you should keep this in mind. Now, Now that we've covered the environment, let's talk about how the environment changes our engine performance. Aerodynamically speaking, we've already looked at it, and we know that with decreasing density, we have less lift generation. Okay, so aerodynamically, the higher we go, the less performant, or the less performance we can expect out of our aircraft in terms of lift generation. And a similar effect we have in terms of engine performance. Now, this is for a piston engine. And if you remember one of our first lessons, we showed you this graph, how horsepower and thrust behave, or with regards to speed. So for example, the faster I fly, my horsepower slightly increased, is more or less, constant, you could say. And my thrust goes down the faster I fly. Now, what altitude does is it decreases the available manifold pressure, and for combustion to happen efficiently, and you need a high pressure. Now, if less manifold pressure is available because the outside pressure is decreasing rapidly, the engine performance is going to go down. So this behavior with regards to speed is also found when we fly at higher altitudes. However, the overall performance output with regards to horsepower and thrust are going to be lower than at a lower altitude. Bear in mind that the altitude increases downwards to show that we have lower performance values as we go higher. Okay, this is important to remember. So you can, this is also when you look at your manifold pressure gauge, that if you leave your power settings constant and you climb, you will see that your manifold pressure goes down, 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 down. And at some point, even if you push full throttle, you will not reach the manifold pressures, the maximum manifold pressures that you are used to from lower altitudes anymore, because the outside air pressure is just too low for the superchargers to fully compensate for it. Alright, so now we've looked at the aircraft's engine performance and how it's influenced by the environment. Let's look at the aircraft's aerodynamic performance, how it's influenced by the environment, or in other words, how can we gauge our aircraft's performance in the environment using the tools and instruments that we have at our disposal in the cockpit. And in order to get an idea how our aircraft behaves aerodynamically, we simply use our airspeed indicator. Why? Because we learned in one of the previous lessons that speed, our aircraft's speed, directly correlates to the lift that we generate. And if we keep everything else constant, like our altitude, for example, that we are currently flying at, then we can vary our lift by varying our speed and also our angle of attack. But we are looking at speed for now. Okay, now remember, airspeed indicator is your best friend in order to determine how well your aircraft currently performs aerodynamically. So for example, if you're close to your stall speed, indicated airspeed, you know, okay, there is not much that can now be done in terms of maneuvering, right? Because we're about to stall. So we cannot fly a tight turn, for example. Okay, now, in order to understand how our airspeed indicator tells us how our aircraft performs aerodynamically, so to speak, we need to understand how the airspeed indicator works. The airspeed indicator shows us the indicated airspeed. The term simply comes from the fact that the airspeed that's shown on the dial, that's why we call it indicated airspeed. And in order to measure our airspeed, we use Bernoulli's principle again, because we know, or Bernoulli's principle states that the total pressure along a streamline, so imagine we're flying at constant altitude, in a constant direction along this streamline, our static pressure and our dynamic pressure that in sum yield our total pressure is constant. So the sum of static and dynamic pressure is always constant. And the dynamic pressure being directly dependent on air density and airspeed squared. So this is the equation that you know for the dynamic pressure. Now, we can use this equation to determine from the dynamic pressure our airspeed. And because of Bernoulli's principal equation, we can write the dynamic pressure as the difference between the total pressure and the static pressure. We just move static pressure to the left of this equation, and then we have total pressure minus static pressure equals dynamic pressure. We can plug this into this equation and solve for airspeed, and then we end up with this. And this is essentially exactly what your airspeed indicator does. It measures the total pressure via your pitot tube. It's also called a stagnation pressure because the air rams, so to speak, into the pitot tube and is stopped to zero speed, so to speak. And the pitot tube also measures static pressure. It has two pressure ports, the total pressure port that is facing into the airflow and the static pressure port that is facing perpendicular to the airflow. And then these pressures are, let's say, transferred to the mechanics of our airspeed indicator. And what the airspeed indicator does, it measures the differential pressure between our total pressure and our static pressure, and hence determines our dynamic pressure. And then, now that we know the dynamic pressure, we can correlate that to a respective airspeed. In order to do that, as you can see, we need to assume a certain density value. So, because density appears here in this equation. So this is our dynamic pressure, the pressure difference, but there's also density. So what air density do we use? Well, we use the air density at main sea level as our reference density, because we don't, at least in these aircraft, the old aircraft, we don't have computers or measurement tools on board that can measure the aircraft density and then correct the value, for example, to indicate a true airspeed. So the instrument is just calibrated for our air density at mean sea level, and that's what we plug in, no matter how high we fly. And then we have this relationship between our measured delta pressure or dynamic pressure and this coefficient here, and we map what we measure to a certain speed. So we create a table, if you will, that this delta pressure equals to this speed, this delta pressure equals to this speed, this delta pressure equals to that speed, and the reference is always the same. It's our density, air density at mean sea level. And now what the indicator basically does, it transfers this table into a visual representation. So when the instrument basically measures a certain dynamic pressure or delta pressure, it will show the speed that we mapped to it. And important is that the airspeed indicator, as it's found in a warbird, for example, and many general aviation aircraft, maps one pressure value to one speed. So if you measure a certain pressure P, it always correlates to an indicated speed V. If you measure another pressure Q or whiskey or whatever, that will correlate to a different speed. But there's always this one-to-one correlation, and that's important in order to understand how it then behaves when we go up in altitude. And this is exactly the question we want to answer now. Now that we know how the airspeed indicator in principle works, we want to understand how it behaves when we change altitude. So, and when we address this question, we can also answer the question, what is the difference between indicated airspeed and true airspeed? Now, as I've pointed it out before, the air density that's used to map our pressure to a respective speed is always the same, and it's the mean, the air density at mean sea level. It's one specific value. For example, the value that comes from our standard atmospheric model, but it's one specific value. Now, if we look at this equation here, what happens if we change things up? Now, let's assume we are flying at a constant altitude first. Then, of course, we have a certain air density, and if that altitude happens to be mean sea level, for example, then our indicated airspeed is exactly equivalent to our true airspeed, because the density, the reference density that we use for the mapping, is exactly the same. Okay? But as we go higher, this density value will decrease according to our atmosphere and, for example, the standard atmospheric model. Now, if we were to measure the same pressure difference with our device, but we have a decreased density, our speed is increased. So we fly truly faster than we would if we measure the same pressure difference at a lower altitude. The reason for this is rather simple. In order to achieve the same measured pressure difference at a higher altitude where density is lower, we need to fly faster, and that comes directly from the equation for our dynamic pressure. So if you look at this equation and you see that rho goes down, we need to increase v squared to measure the same dynamic pressure, which we measure as this delta pressure here, because this is our dynamic pressure. Okay? That is why true airspeed is higher than indicated airspeed as we go higher in altitude. There are rules of thumb that you can use to convert indicated airspeed to true airspeed. For our combat, that is not very relevant, so I'm not getting into that. For navigation purposes, that will be a bit more relevant. But this is simply the reason. So if, as I said, if we want to measure the same pressure difference at a higher altitude where we have a lower air density, we need to fly faster. Okay? And this is why true airspeed increases with altitude, even though your indicated airspeed would stay the same or even decreases. Now, what happens if we fly at constant speed? For example, we actually fly at constant speed, but what happens to our indication? Same principle here. As if we actively fly at the same actual speed or true airspeed at a lower altitude and a high altitude, our airspeed indicator, indicated airspeed, as we go higher, will show a lower value. Okay, so our indicated airspeed will be lower than our true airspeed actually is, even though we didn't change the speed from flying at a lower altitude and flying at a higher altitude. But the indicated airspeed that's indicated will be lower, and this is why true airspeed and indicated airspeed diverge from one another the higher we go. And the reason for this is simple. The instrument is calibrated for our mean sea level air density. Now, as we go higher, we will, if we maintain the speed constant, here, and from this equation you can see this very nicely. If we maintain a constant speed and we go higher, then only rho, the air density, will go down, and effectively our dynamic pressure will go down. So the measured pressure difference is smaller. And because we have this one-to-one mapping where we say we measure this pressure at mean sea level, that means we fly at this speed. We measure this pressure at mean sea level, that means we fly at this speed, means that depending on what pressure difference we measure, we will get a respective speed indication. And since the air is less dense up high, the pressure difference measured if we maintain a constant speed is smaller than compared to a lower altitude. The indicated speed will also decrease or be smaller than it actually is. And this is why you see indicated airspeed dropping down. Now you might wonder why do we want to use indicated airspeed then? Because it's unreliable in terms of showing you what your actual speed is, especially the higher we go. Okay, and we will look at this question in a second. Just to illustrate the point that I've just mentioned, here the example visualized. Okay, a pressure P1 that I measure is always correlated to a speed V1. A pressure P3, for example, that I measure is always correlated to a speed V3. And V3 being higher, for example, than V1, because we assume that the pressure values go up as we go down this line here. So if we measure at mean sea level our pressure, then our indicated airspeed is our true airspeed, because the reference or the air density that we use is the same. But if we measure, for example, at 15,000 feet, for the same actual true airspeed as down low, we will probably measure P1, which is smaller than P3, and hence our airspeed that is indicated will be smaller. So the indicated airspeed is always smaller than the true airspeed as we go higher. Okay? Because the air density changes. And this air density change is not accounted for in the working principle of our airspeed indicator. Okay, now I know that might be a bit difficult to digest, but I hope I could carry the point across. Okay, now, why is this relevant? Why do we need indicated airspeed, or why do we insist on indicated airspeed? Well, indicated airspeed tells us how our aircraft behaves aerodynamically, for the following reason. If we look at our lift equation here, we can see that we have our dynamic pressure here. And as our dynamic pressure goes down, our generated lift will go down. Now we've already established if we fly at the same true airspeed at a lower altitude and a higher altitude, at the higher altitude we will have a smaller dynamic pressure and hence less lift available. And the indicated airspeed tells you what your current dynamic pressure is with respect to the mean sea level value, because the indicator is calibrated for the mean sea level values of your dynamic pressure. Okay, so in short, if you fly at 250 kph, for example, or miles per hour, it doesn't matter, 250 kph indicated airspeed at 20,000 feet, the aircraft will behave more or less the same way as it would if you were flying 250 kph indicated airspeed at mean sea level, because we have the same dynamic pressure and hence the same or equivalent amount of lift that we generate. Okay? And as you go higher and your indicated airspeed approaches maybe your stall speed, and that's also what you experience as you fly high, your aircraft behaves as if you fly near the stall region. And this is the simple reason for it, because the dynamic pressure goes down, and hence our lift goes down. Okay, so the summary of what we've just established in terms of how performance is influenced by the environment is written here. So our engine performance is decreased at higher altitudes. We have less specific excess power available. We have less horsepower available, and also our thrust output will decrease compared to lower altitudes. Due to the lower specific excess power, that gives us an idea, how of our climb performance. Our climb performance is also reduced at higher altitudes. And from an aerodynamics point of view, as just mentioned, the higher we fly, if we maintain a constant true airspeed, the less lift we generate, and hence the less aerodynamic performance, so to speak, we get out of our aircraft. And that's also the reason why aircraft at some point have a service ceiling, because the dynamic pressure gets so low that it's just enough that, in straight flight to maintain or counter the aircraft's weight. Okay, so when the air density goes so low that at full power settings and maximum angle of attack, and you can just manage to get enough dynamic pressure to generate enough lift to counter your weight, and that would be your absolute service ceiling. You cannot go any higher than that, because if the air density decreases further, you don't have enough lift force to sustain the weight. Okay, which is also why it's easier to fly higher when you're lighter. Okay, now this is the point that I've already hopefully got across to you. So for you as a pilot, what is important and why we still use today indicated airspeed is because it tells us exactly how our aircraft performs aerodynamically. And for us, what is important to know is how much speed margin are we away from our stall region. Okay? For instance, BF 109 at main sea level with an indicated airspeed of 250 kph behaves more or less the same way as flying this BF 109 at 7,000 meters at the same indicated airspeed. That is also why our approach speeds are always the same, whether I approach an airbase at mean sea level or high up in the mountains. We don't need to adjust our stall speeds, because if we were to indicate true airspeeds, the stall speeds will be different depending on our altitude, and that's obviously quite confusing. So indicated airspeed is very relevant in judging our aircraft performance, the reasons why we've just established. And just remember this, from a pilot's perspective, your indicated airspeed tells you how your aircraft performs aerodynamically, because it tells you how far away you are from your stall margin. And if you fly at an altitude where you can just barely manage to stay above your mean sea level flight stall speed, that means your plane is almost at its maximum performance limit in straight flight, and you have reached your service ceiling, for example. Okay, so if you fly up high, keep your indicated airspeed in check. You will notice that it's considerably lower than at lower altitudes at the same power settings, and hence the aircraft, because we know now your indicated airspeed tells you how your aircraft behaves aerodynamically. Just learn, and this is how you can prepare for high altitude flying and fighting, learn how your aircraft behaves at certain indicated airspeeds, for example at mean sea level or close to it, and then that gives you an idea how your aircraft will then behave at the higher altitude, more or less. Okay? Wonderful. Now that we've established how our aircraft performs at higher altitudes, let's derive some rules for our high altitude fighting and how to approach it, and good behaviors at high altitude. And let's start with horizontal maneuvering. Now, as we've seen, engine and turn performance are decreased because the lift output is decreased, and hence we will fly wider turns. We won't get the same turn rate as we get down low because we have less thrust available to counter our drag. So for high altitude flying and horizontal maneuvering specifically, any maneuvering for that matter, it is crucial to really watch your airspeed. If you see that your aircraft is approaching the level flight stall speed at low altitude, you know you're approaching your maximum ceiling, for example. And then you also know you cannot get any good turn performance out of your aircraft. Okay? So your aircraft can only sustain smaller bank angles. And smaller bank angles means smaller load factor and hence a lower turn rate. We've established turn performance in previous videos. So that means when you fly up high, be patient. Give your aircraft the space it needs to make your maneuvers and watch your airspeed. Keep a specific margin or a sufficient enough margin between your level flight stall speed and the speed that you can achieve at a specific altitude. Okay. And if you're close to your aircraft service ceiling, rather stay in a horizontal maneuvering kind of situation and do avoid spending your energy by going vertical, for example, in a dive and so on and so forth, because you can't really go much further up. So preserve your energy by maneuvering horizontally. So good practices when flying at altitude. Even more important than down low, fly coordinated. Keep your ball centered to reduce your drag because of limited or reduced engine performance. All changes that you want to do your current flight path, do it gently. Give your aircraft the time it needs to perform a smooth maneuver. Because energy lost at high altitude is so much more difficult to gain compared to lower altitudes because your aircraft is operating or more prone or likely to operate at its limits, even at low bank angles already as established. And avoid stalling your airframe at all costs, because the higher you go, the longer it will take and the more altitude you will lose to recover from a stall or a spin. So don't do that. Okay? And also keep your speed as high as possible. So you can fly at lower AOAs or angles of attack during your maneuvering. Speed is key at high altitudes. With regards to vertical maneuvering, as established, your specific engine power that's available to you is lower, so you have worse climb rates than you have down low. And you also need to increase your airspeed further to perform a vertical maneuver. Sometimes a slight dive is necessary to get to the necessary speeds to perform a vertical maneuver, for example, a looping at 20,000 feet. Okay, and because your aerodynamic speed, so to speak, or indicated airspeed is lower than it is at lower altitudes, you need more time because you need to get to similar indicated airspeeds, for example, to perform your looping maneuver, as you would at lower altitudes. For example, if you start or initiate a looping at 450 kph, for example, at lower altitudes, because you've established that in your airframe, you can do that comfortably. You would also have to reach 450 kph indicated at a higher altitude to perform the same looping. And you can see why this is a problem and why vertical maneuvering gets more and more difficult the higher you go. Yeah. Which is also why altitude is lost so much quicker than gained, especially when you're up high. So bear in mind when you find a target down low and you want to dive down on it, you might be surprised how much more turn radius you require for this split S or this dive turn, if you will, vertical turn, to get onto this Bandit 6 And you might even be surprised that you undershoot the guy because the altitude difference that you have available is not enough to perform that turn. And again, good practices also during vertical maneuvering, coordinated flying, smooth introduction of changes, and at best do not get too slow, especially if you perform a power climb, recover before you get too slow, and then you need a lot of altitude again to recover from this power climb. All right, and yeah, so with regards to energy management, obviously the higher you are, the more careful you need to watch over your energy, and the better you need to preserve it, because it's so much more difficult to get it back. So even a higher degree of discipline is required to fly up high and to not waste energy unnecessarily. Keep it as high as possible. Do only invest it if it's absolutely sure that your investment is worth it. For example, you get a good firing solution on the Bandit. And because you're at high altitudes anyway, at high power settings, you operate at low indicated airspeeds, there is not much speed that you can transfer really into altitude. Moreover, because your climb performance is reduced, so be mindful. If you want to transfer speed into altitude, you will have to need or consider longer vertical distances to do that. Also, energy conserving maneuvers like high and low yo-yos are less and less possible or more difficult to perform because of your reduced climb performance. You see there's a repeating pattern there. So, which is why my advice personally is, if you want to fly energy efficient at high altitudes, especially if you're close to your service ceiling, avoid vertical maneuvering, stay horizontal, keep your speed high, fly smooth turns, and when you have a good opportunity to dive onto a Bandit, then do that. But take your time. Okay, because once you are at an energy disadvantage, it's very difficult to get out of there. Okay, and at high altitudes, because your indicated airspeed is low, if you find yourself at an energy disadvantage, it's also more difficult to react to a threat defensively. Because if you fly at an indicated airspeed that is close to your stall speed, there's not much room for maneuvering, right? Not much energy available for tight brake turns or maneuvering or so on and so forth. And if you have to roll over, do a split S, don't be surprised if you lose 2,000 meters of altitude in no time just to perform that split S and find yourself even much more lower than you were before the engagement. Okay, and again, fly coordinated, smooth introduction of changes. I repeat this so often because it's very important. Don't get too slow, manage your speed. And at high altitudes, even more important, fly or start engagements at a higher energy level, because it's much more difficult for the other guy to defend when you have the energy advantage. If you fly up high and you don't have the energy advantage over a guy above you, you suffer even more compared to down low. Okay? Learn to fly your plane at the limit, because you will be eventually at the limit as you get close to your service ceiling, and you will reach your stall speeds rather quickly, even in rather shallow turns. So be prepared for that. Okay, now that we've covered good practices for high altitude flying, let's see how this translates to high altitude flying, in terms of practical examples. So this is where this episode ends, and the practical examples we are going to look at in the next episode. I will provide live commentary to, actual combat footage from the II.I Project Overlord server which was recorded during various engagements at high altitude against P-51 Mustangs in the Bf 109 K4. But the principles apply to any aircraft. All right, I hope that lesson was useful for you, especially because there's not much on high altitude flying out there on the web. and we thought this is a great addition to the overall knowledge that is shared over the internet. So we hope you enjoyed this episode. Stay tuned for the next one. Thanks for listening and tuning in. Killer Fliege out.